Kia ora and welcome to this video, question 3 of the 2018 Scholl Calc exam. The first question is an integral which a substitution will help you with. The second is an economics example of integration. Quite an interesting problem actually if you look a little bit deeper into it. And then the third problem is a differential equation where you have to form the equation to start. And it involves related rates to narrow down the variables. So a good step up from your standard level 3 DE. Okay, so for the first question, we could use integration by parts because we're integrating a product, but a simple substitution actually does work. The idea is that there's two things under the square root and we can't split them up. But if we make that our substitution, then we turn it into only having one thing under the square root and we can algebraically simplify the problem. So we've got the integral between x equals 0 and x equals 5. 2x minus 5 times square root 2x plus 5 dx. And we're going to let u equal 2x plus 5. It means that du dx is equal to 2, or du is equal to 2 times dx. And then that replaces that bit, square root u. Dx is equal to du over 2. And the 2x minus 5 is u minus 10. So if I take away 10 from this side, I get 2x minus 5. I need to take away 10 from there as well, so I get u minus 10. And that's the case with all integration by substitution problems. The idea is that you replace everything in the question with the new variable, including the limits. So when x is equal to 0, u is equal to 5. And when x is equal to 5, u is equal to 15. And then we can algebraically we can expand this because we've got u times the square root of u. We've got a half that we can pull out the front of the integral. U times square root u is u to the power 3 over 2. And 10 times square root u is 10 to the half. Okay, so we're integrating that. U to the 5 over 2 divided by 5 over 2, so 2/5, and u to the half goes up to u to the 3 over 2, and we're dividing by 3 over 2 or timesing by 2/3. The 2/3 will go with the 10 to make 20 over 3. And then we sub in 15 and sub in 5. Now that will give us an answer of 6.7225, and you can verify that. And of course, a graphics calculator will get that answer for you. You can just substitute the original problem in, but we must show the integration when solving it. Okay, the second question is an interesting one. Why would this method not work if we did this integral here where the only difference is the plus and minus splitting around? So you can actually follow through the process. You could go, alrighty, integral between 0 and 5, 2x plus 5 times root 2x minus 5. Make the substitution, 2x minus 5. So dx is 2 du over 2, that's square root u again, and then 2x plus 5 is u plus 10. So everything looks happy days so far. And then our limits, negative 5 there and 5 there. And we can see we're going to have a problem because we're going to have to substitute a negative number into the, not into there, so we're not subbing into there. We've got to anti-diff it. Why is my pen lagging? Oh my goodness. But you know, the next step would be integrating -5 to 5 u to the 3 over 2 plus 10 u to the half, which have got square roots in them. And u to the 5 over 2, 2/5, u to the 3 over 2, 20 over 3. So everything's exactly the same, but then the problem comes in this next step when we need to sub in the limits, because that bottom limit is negative, and subbing it into there we've got to square root it and we get imaginary values. So if you just said, you know, this doesn't work, it doesn't give you a real number, it's probably not sufficient. We need to go back to the original question and go, why is that happening? And it's simply, if you look at this graph, the graph of this, it's not defined for any x value less than 5 over 2 or 2.5. So the interval that we're integrating over includes values where the integral is not defined. So answer to the question would be integral is not defined for x is less than 5 over 2, which is actually half the region of the interval that we're trying to integrate over. Okay, second problem gives you an unfamiliar integral to work out. If you read through the problem, we've got to find two areas: the area between the curve and the equality diagonal, and the area beneath the equality diagonal. Now, the graph is actually misleading. If you substitute 100 in for the x value of both of these expressions, we get two completely different y values. When we sum in 100, we get y is equal to b minus 1 over b, which is the same as x squared minus 1 over bx squared plus 1 over bx. If we sub in 100 in there, we still have stuff to do with b's in it, but if we sub in 100 into the other function, we just get y is equal to 100. And we sub into there. So the graph is misleading because actually the limit there should be x equals 1. It should be a proportion. So 100% is a probability of 1. And if we sub in x equals 1 into this expression, we get y is equal to 1 minus 1 over b plus 1 over b, which equals 1. Okay, so the axes are labelled incorrectly, which isn't helpful. But I think they've done that just so you can get your head around, you know, how the problem actually works in terms of the context. So if you had a population where the distribution of income followed the function that they've given, which is a parabola, then if we look at some particular values, for example here, 40% of the country earns 18% of the income, and say, I don't know, 60% of the country, of the people that live in the country, earn the lowest 40% of the income. So it's not a equal society. And if you had y is equal to x, that would be 50% of the country earn 50% of the money, 100% of the country earn 100% of the money. So everyone would be fair, a fair society. So that's where this coefficient of inequality comes in. If the area between the curve and the diagonal is exactly the same as the area beneath the diagonal, that would mean the curve is y equals x. There's no area between. And so a coefficient of inequality of 0 would say that society is fair. and if the area between the equality diagonal is really large, then that ratio is, how is that ratio going to change? The area beneath the equality diagonal is always, it's just the area of a triangle. And if we, okay, that's 1, and that's 1. So the area below it is a half base times height, so a half. And it's not possible for the curve could do something like this, for example. Have larger area. So the larger the numerator is, because the denominator is a constant, would mean that inequality is, the coefficient is higher. So we've got a more unequal society. Okay, obviously in an exam situation you don't really have time to think so much about that. You just jump straight into the problem. But when you're reflecting on exam questions, you can often think about the structure of the formula. Okay, so we've got to find the area between the curve and the equality diagonal. So we're integrating between 0 and 1, the top function x minus the bottom function, which is the parabola, b minus 1 over b all times x squared plus 1 over bx. Okay, that's the area between. Alrighty, so we have a linear function, x there in the front. We've also got the 1 over bx. So if we put that together before we do the integration, it makes us have one less term to deal with. Just like they've done there with the quadratic term. And b is just a constant we're trying to determine. So if we integrate the linear function, the constant just stays in the front. Integrate the quadratic function, x cubed over 3, and that's between 1 and 0. Be careful, we're subbing 1 and 0 into the x values. So we get 1 minus 1 over b all over 2 minus, I'm going to write that b minus 1 over b is 1 minus 1 over b over 3, and then zeros, they cancel. Okay, so that's the area between. Therefore, coefficient is this stuff. Remember that that's in the numerator of the fraction. But we've got the area beneath the equality diagonal, that triangle, which is we've already found as an area of a half. All divided by 1/2, 20 over 63. So we just need to solve this equation. Look, I recommend when anything's involving fractions, we get rid of the fractions. So if I first up times both sides by 1/2, it's going to be 10 over 63. Then I times everything through by 6 to get rid of the 2 and the 3. So it's going to be 3 times 1 minus 1 over b minus 2 times 1 minus 1 over b equals 60 over 63. And then I've got 3 minus 2 is 1, minus 3 over b plus 2 over b is minus 1 over b. One minus 60 over 63 equals 1 over b. 3 over 63 is 1 over b. So b is 63 over 3, which is equal to 21. Now you don't get that value of b if you use the limits of 0 to 100, but then the functions don't actually meet when x is equal to 100, so you have a bit of an issue with the problem if you do that. But there probably would have been partial credit for that, given that it was a mistake on the graph. Okay, the third question is a differential equation. We're told that we've got water in a tank that's emptying. So if we call the water in the tank some volume V, then we know that dV dt is a negative number. The rate that the volume is coming out is negative. We know, before we even get to rates, we know that the volume of water in that tank there is pi times radius squared times height. But the question's talking, is set up in terms of diameters. So we get pi times capital D over 2 squared times height. That's the volume of water. And the question's asking us for the time taken for the level to drop from H1 to H2. So we know that the volume depends on time. The rate that the volume is leaving the tank is the same as the rate of volume going out of the spout. Now that's going to be dependent on how big the spout is, as to how much water can flow through it, and also the speed in which the water flows out of it, which we see as proportional, or it's got a h in it. G's gravity, it's a constant, but that kind of should make sense to you. Like if there's more water in the tank, the force behind it is going to make the water go out the spout quick. But if there's less water in the tank, so the h is smaller, the speed in which it goes out is slower. If you've ever had a water cooler, like I do in the boarding hostel that I'm in, when it gets empty, it's very, very slow to fill up your water bottle, but when it's full, you get water pretty quickly. Okay, so dV dt is, if we imagine the spout here, we've got some area pi times little d over 2 squared. That's the area that the water can go out. And then in a small unit of time, this is how much water would go out in, say, 1 second. You know that, you know the relationship between distance and speed. So we've got velocity is distance over time. So what we have there is the dV dt is that area of the spout times the speed that the water goes out. So for example, if it's going out at 2 meters per second, then in 1 second that would be 2 meters, and so the volume, it's a small cylinder, right? So you've got the area times the height. So that's why we multiply by the speed there. Excuse me. But the problem with this differential equation that we've got is it's got 3 variables in it: volume, time, and speed. So we replace the speed bit with root 2gh. Remembering that little d is just a constant. And we've still got a problem because this differential equation's still got 3 variables in it. G is a constant, so we can pull that out as root 2g. But we've still got h to the half. Okay, so still 3 variables. And this is where related rates helps us. Because if we go back to this original equation that we had set up and how the volume depended on the height, we can find dV dH from this one. dV dH is equal to pi times capital D over 2 all squared. It's a constant times h. When we differentiate it, we just have the constant left. and then dv dh multiplied by dh dt, so it gives us dv dt. So that replaces our dv dt. And now we've only got two variables in there, because dvdh, I should have done that all in one go, dvdh is actually equal to pi times capital D over 2 squared, and the only variables left are little h and little t. So we can separate the variables here. We can cancel pi on both sides. We can cancel a 2 squared on both sides of the denominator, and we can separate the variables as 1 over h to the half dh, little d squared over capital D squared root 2g dt goes up to the top right, integral. Now the question is saying, show the time taken for the level of the water to drop from H1 to H2. So if I replace that with H1 and H2, and that with T1 and T2, we're going to get the change of time expression in there, and we're going to get the change in height expression. So if I integrate, h to the minus a half integrates to h to the half divided by half, or 2. There. And then all of that's just one giant constant, so when I integrate it I get a t. And I can sub in the two different time values that we're measuring and find the two different height values at those points. So we've got 2 square root h2 minus, and that's a common factor there, minus root h1, and then little d squared over capital D squared, which I should actually write as little d over capital D all squared, because that's what the problem wants us to do, and then 2t, t2 minus t1. Okay, and the question asks us for the time taken, which is going to be t2 minus t1. So we just need to make that the subject of this equation. For t2 minus t1, which is the change in time, is equal to 2 square root h2 minus root h1 over little d over capital D all squared root 2g. Okay, now it doesn't look quite like the expression we want. The interesting thing is actually I've got my h2 and my h1 around the wrong way. Now let's think about that. H2, the second height value, is going to be smaller than the first height value because the tank's leaking. And if I look back at my dv/dt equation, it's actually slightly wrong, because pi, d over 2, 2g, all of those are positive, and the height's positive, which means I should have had a negative in that. Okay, I should have had a negative there, which I could put on that left-hand side. It's got to be somewhere. And that's why my h2 and h1 come out the wrong way around here. But look, it was only a minor error. You could just argue that the change in height is negative between that time. But we do want to prove exactly what the thing says. Okay, and then we just have to fiddle around with this to get it in the right format. So we're dividing by d over d all squared. That's the same as timesing by the reciprocal. And then we've got 2 over root 2, 2 to the 1 divided by 2 to the half there's a root 2 on the top, and there's a g on the bottom still. So root 2 over g. So this is probably the messiest I've set out a video so far. And then we've got root h2 minus root h1. Is that what we wanted? Yes. Oh, why was my h2? Oh, because I didn't change it. Change it there, change it there, change it there, change it there. My bad. Alright, now we're good. Square box, smiley face, happy days. Not too bad for a question 4. The problems definitely were harder than level 3, as often is the case, but 3A, reasonable substitution, 3B, a couple of areas you had to find, but the limits needed a little bit of care. And that third one's definitely a harder one because it involved related rates, but not too bad overall. See you in the next video.